Think about the last time you were in real pain. Not discomfort, not soreness. The kind of pain that takes over everything, that makes it impossible to think about anything else, that reduces the entire world to a single point in your body. Now think about what that experience actually is. Not philosophically, physically. Your brain receiving a signal, your nervous system flagging damage. A cascade of chemicals that evolved over hundreds of millions of years, for one purpose: to make you stop doing whatever is causing harm. That system is ancient, far older than you, far older than mammals, far older even than dinosaurs. Which means the question isn't really whether dinosaurs felt pain. The more uncomfortable question is how similar that pain was to yours. Whether 100 million years ago, an animal with no language and no concept of medicine experienced something that, in its most essential form, you would recognize. The obvious assumption is that pain scales with intelligence, that the more complex the brain, the richer the experience of suffering. That a dinosaur, with its relatively small cerebral cortex, would have experienced something so basic and muted compared to human pain that the comparison barely holds. But that assumption is exactly what modern pain science has spent the last 2 decades dismantling. The real question isn't whether dinosaurs had the brain power for complex suffering. The better question is, which parts of the pain system actually require a complex brain, and which parts are so old that complexity is irrelevant? The answer splits pain into 2 things that most people never separate. And once you see the split, the dinosaur question becomes genuinely strange. In 2003, neuroscientist Jaak Panksepp, whose decades of work on animal emotion fundamentally changed how biology thinks about non-human experience, published research identifying what he called the panic system, a set of neural circuits responsible for the affective, emotional dimension of pain, not the sensation of tissue damage, the suffering that accompanies it. What Panksepp found was that these circuits are located in the subcortical brain, the ancient, evolutionarily conserved structures that sit beneath the cerebral cortex, not in the neocortex, which is the part that varies dramatically across species and is responsible for higher cognition. In the deep brain, the part that fish have, the part that reptiles have, the part that was fully operational long before the first dinosaur walked the earth. This distinction matters because it separates nociception, the mechanical detection of tissue damage, which nearly all animals possess, from the suffering component, the "this is bad and I need it to stop" experience. Panksepp's work suggested that the suffering component doesn't require a complex brain at all. It requires the subcortical structures that evolution had already perfected 400 million years ago. Start with what the fossil record tells us directly. Dinosaur bones preserve evidence of injury and healing in extraordinary detail. Paleontologists have identified healed fractures, bone infections, tumors, and arthritic joint degeneration in specimens across dozens of species. A hadrosaur specimen discovered in South Dakota showed evidence of a severe bone infection, osteomyelitis, that would have caused chronic, debilitating pain in any modern animal with similar anatomy. The bone had been remodeling around the infection for what appeared to be months, possibly years. The animal had been living with it, surviving despite it. That survival tells us something. An animal experiencing nothing, no signal, no suffering, has no particular reason to alter its behavior, to protect a damaged limb. But the bone remodeling patterns in dinosaur injury specimens show exactly the kind of compensation behaviors we see in modern animals managing chronic pain: weight redistribution, changed gait, protective posturing. The body was responding to something. Now think about the neurochemistry. The opioid system, the brain's primary mechanism for modulating pain, the same system that responds to morphine, to endorphins, to the body's own pain relief, is not a mammalian invention. It predates vertebrates entirely. Opioid receptors have been identified in species as ancient as sea slugs. Every dinosaur that ever lived had a fully functional opioid system. Their bodies could generate their own pain relief, which means their bodies had something to relieve. But here's what's really interesting. In 2021, a study published in Science Advances analyzed the nervous system architecture of archosaurs, the group that includes both crocodilians and birds, the living relatives of dinosaurs, and found nociceptive fiber densities in skin tissue comparable to those of mammals. The nerve endings responsible for detecting heat, pressure, and chemical damage were present, dense, and functionally similar. The hardware was there, not a diminished version. The same hardware, doing the same job, in animals whose lineage connects directly to the Mesozoic. A triceratops gored by another triceratops felt the impact through the same class of nerve fibers that would register the same injury in a human. The signal traveled, the brain received it, the opioid system responded. Something happened that, at its most basic biological level, was the same event. But here's the thing. The question we started with, did dinosaurs feel pain the way we do? Turns out to be two separate questions, pretending to be one. Did they feel the signal? Almost certainly yes. The nociceptive hardware is ancient and conserved. It was working in the Cretaceous the same way it works now. Did they suffer the way we suffer, with the cognitive overlay, the memory of past pain, the anticipation of future pain, the narrative of what the injury means for their life? That's where the answer becomes genuinely uncertain. And that uncertainty is more interesting than either a clean yes or a clean no. Because it means pain, real pain, the kind that changes behavior and drives survival, doesn't require language or self-awareness or a concept of the future. It requires something far older, something that was already old when the dinosaurs were young. There is a triceratops specimen in a museum in Denver with a healed horn fracture, the bone knitted back together over months. The animal survived, went on living. We don't know what it experienced while that bone was healing. We don't have the language for what happens in a nervous system that old, processing a signal that ancient. But the bone healed, which means the animal kept going despite something that, in every biological system we understand, would have been a reason to stop. Whatever that was, whatever moved through that nervous system 68 million years ago, it was not nothing.